the following three components, U, V, and W. Where A and B are constants. So the first question is, find the equation of a path line passing through this one. The second question, find the equation of not equation, find an expression of the velocity potential if exists. And number three, find the projections of the streamline streamlines rather on the XY plane. So let us try to look into the answers to these one by one. The first question is related to the equation of the path line. And equation of the path line is something which is very straightforward. It is the locus of fluid particle over a period of time. So as you recall that in place of U we will write dx dt. This is actually dx particle dt. This is equal to A into x plus y. Dy dt similarly is A into x minus y. And so in terms of the z, it is very trivial. In terms of x and y, we can rearrange. So we can write first of all the z dependence in a way which is independent of how the trajectory varies in the xy plane, because you can just integrate it with respect to time and you will get z is equal to some b into t plus a constant c. So that is how the z coordinate will vary, and it has nothing to do with x and y. So x and y interdependence can be worked out independently. So to do that, what we will do is first we will differentiate it once more with respect to time. So if we do that, we will get so the objective of writing it in this way is that now if you look into these expressions, so dx dt is A into x plus y and dy dt is A into x minus y. So if you subtract these two, a into x gets eliminated, and you will get a into y minus of minus a into y. So that means ultimately it is 2 into a into y into another a, which was there in the front. So it is d2y dt2 is equal to 2a square y. So if we now, I'm just writing it here. So if we now write the equation d2y dt2 minus 2a square y equal to 0. So now this is a simple homogeneous second order ordinary differential equation. So you can assume y equal to e to the power mt as the trial solution. I will show you some interesting thing which will come as a consequence of mathematics, but something which you will not get an insight into if you do not look into some of the critical aspects of the problem very carefully. So if you make a second derivative of this, this will be m square minus 2a square. This is equal to 0. So m is equal to plus minus square root of 2a. Okay. So the solution or the equation, again, I'm just freeing up some space here to write. So it is a linear combination of the two solutions. That means y equal to c1 e to the power root 2ay plus c2 e to the power minus root 2ay. Sorry, not y, t. Okay. So now you have the conditions at time equal to 0. You will have what is given at time equal to 0 or at time equal to t0. X equal to x0 and y equal to y0. So that means y0 is equal to c1 e to the power root 2a t0 plus c2 e to the power minus root 2a t0. So this is a condition on y, and we can find out a condition on x. It is quite straightforward. You can use, for example, so if this is y, so from any of these equations, say this one, you can find out an expression for x, or in fact this one will be easier because v will is dy dt. So we will write, sorry, dy dt from this equation, dy dt is equal to a into x minus y. So dy dt is c1 root 2a e to the power root 2at minus c2 root 2a e to the power minus root 2at. Okay. So this is dy dt. This is equal to a into x minus y. So if you substitute the values of x at time equal to t0, so you will get similar equation as this one. So let us write that, because it is something that is going to lead us to the values of C1 and C2. So let us just substitute here. First of all, you can cancel a from both sides. So you will have x is equal to C1 into, this is 1 and plus root 2. 1 plus root 2 e to the power of root 2at plus C2 into 1 minus root 2 e to the power minus root 2at from this equation. So at time equal to t0, you have x equal to x0. So let us put that here, so that x0 is equal to C1 into 1 plus root 2 e to the power root 2a t0 plus C2 into 1 minus root 2 into e to the power minus root 2a t0. This is x0 y0. Okay. So when you have this x0 y0, what you can do is simply you can find out C1 and C2 from these two equations. But let us see a very interesting case. So let us take an example. So I mean, general case is very straightforward. From these two equations, two unknowns, you can in principle find out C1 and C2. Let us consider a very interesting special case. So the special case is t0 is equal to 0, that is at time equal to 0, x0 equal to 0 and y0 equal to 0. That means the particle is at origin. So let us put the values here. So when you put here, when you put x0 equal to 0 and t0 equal to 0, you will have C1 into 1 plus root 2 plus C2 into 1 minus root 2. This is 0. And again 0 is equal to C1 plus C2. So what can you conclude from this equation? Any one of you? So we are discussing about the equation of a path line, and we have taken a special case that at time equal to 0, the fluid particle was at the origin. So what will be the path line? Any one of you can just tell from here.
The particle stays at the origin.
The particle stays at the origin, right? If it was condition like this, where there is, say, a parametric dependence on some parameter, say A or something, A or B or whatever, then the situation would be that for some values of the parameter, the particle will remain at the origin, and for some other values it will not, because essentially what you are having this in the system of equations is that you have C1 into something plus C2 into something equal to 0 and C1 plus C2 equal to 0. So for non-trivial solution, you should have the determinant of the coefficient of C1 and C2 that is equal to 0. So what it means is that if you write the determinant, here clearly the determinant is non-zero because you have 1 plus root 2 and then 1 minus root 2, 1 and 1. Okay. So this is not equal to 0. So that means only solution is a trivial solution, that is C1 equal to 0, C2 equal to 0. But let us say that instead of these ones we had some parameter, other parameter, then that parameter, the value of that parameter under some circumstance will make this equal to 0, and then it is possible that the particle which is originally at the origin will not remain at the origin over a period of time, and whether it will remain at the origin or not, it will depend on certain other parameters. Here it is just dependent on certain numbers, and since the numbers are not cancelling with the determinant, this is clearly not equal to 0. So what we can see is that now this is a very interesting example where you have the velocity non-zero at all points except 0, 0. But because at 0, 0 the velocity is 0, the particle which is injected there at time equal to 0 is unable to move further, irrespective of whether at all other points the velocity is non-zero. Okay. So this is the first part of the problem. Let us get into the second part.
Sir, but there is a z component of velocity, which is if b is not 0, then particle, if it is starting at
Yes. So that is the obvious thing. That means that what we have written here, I mean, so far, is that in the xy plane it is not moving. So the answer that we were giving is regarding the xy plane. Remember, not the z, because the answer. So it is not a complete answer of the question number 1 that I have given. I have given the answer of the question number 1 so far as the xy plane is concerned. But you are correct for the overall motion, that is the path line. If b is, so here b is a very important parameter. So if b is not equal to 0, that means so doesn't matter what is a, but if b is not equal to 0, if b is not equal to 0, then look at the trajectory which is governed by the W component. That means this one. So what it means is that irrespective of the value of A, the particle, the fluid particle, will move along the Z direction if B is not equal to 0. And it will move by following this. You can find out the value of C, for example, if it is given. So that part was not given actually. That is why I did not extend to that. But let us say it is also given that at t equal to 0, you have Z is equal to 0. So that means C equal to 0. So your equation of the path line will be simply along the Z axis, which is the Z coordinate proportional to t. And here also there is a possibility that irrespective of different possibilities of the value of B, one clear possibility is B equal to 0, and then the particle will stay at the origin from all considerations. The consideration from which I was talking about first, about the particle staying at the origin, is based on the what happens in the xy plane, because our differential equation which we solved was y as a function of t and x as a function of t. We did not bring in w, and because of the interdependence of x and y components of velocity, and z component being like a constant, so this is a very interesting mathematical situation that although it's a three-dimensional flow, but it can be thought of as something in the xy plane superimposed by something along the z-axis. So, the first part of the problem, for that the first subpart was considering the phenomenon in the xy plane, and the second subpart which we have just considered is along the z-axis. Now let us enter into the second part of the second question. So first of all, we have to see whether the velocity potential exists or not. So the velocity potential exists. How will we know whether it exists or not? So what we will do is we will find out the curl of the velocity. And see whether it is a null vector or not. Because if the curl of the velocity vector is a null vector, then it is irrotational flow, and then you can find out what is the vorticity. So to understand that, what we will do is we just substitute the expressions. U is okay. So let us write this. Just a straightforward calculation, but let us see. You have I. So this is 0. J, that will also be 0. That K part, that is A, and minus. So that means this is a null vector. all are 0, all the components are 0. That means it is irrotational flow. So irrotational flow, the velocity potential will exist. So how do you find out the velocity potential? That is the interesting part of the solution, because certain things will come out of it, which is again, we have to be a bit more subtle than the way in which we normally solve these problems in the undergraduate level. So let us look into that. Okay. So if you now integrate this, so remember that when you, so what I have written first is the definition of U in terms of the velocity potential. So this being a null vector means the velocity potential exists. So you can write U in terms of the velocity potentials gradient. So if you integrate now when you integrate, remember, just like partial differentiation, this is called as partial integration. So partial integration means because this was derivative with respect to x, for the integration, x is the only variable and others like y and z are like pseudo constants. They are not actually constants, but with respect to this integration, they are like constants. So with that spirit, if you now integrate it, so x will become x square by 2. For the second term, y is like a constant, and you will have something like a constant of integration. So constant of integration, it is when you are differentiating with respect to x partially, any function of y and z is like a constant. So the constant of integration, this itself could include some constants also, but it's a general form which could have some function of y, some function of z, and some constants. All together, this is f1. Now, if you write the expression for v, so sorry. So if you now integrate it with respect to y, this will be axy minus ay square by 2 plus it will be a function of x and z. And for w, it will be a function of x and y. So now, if you try to compare the three equations, and then they are representing the same phi, right? And therefore, uh, if you compare the three, you will be able to figure out what are F1, F2 and F3 so that all the three expressions are identical. So F1, if you just compare, so this contains Z. So only thing that contains Z is no, this one Bz. F2, uh, this so F1 contains only a function of Y and Z. So here there is one term more. I have missed it. It is minus a y square by 2. So this is function of Y and Z. Right? F2 will be a function of X and Z. So function of X is ax square by 2. And function of Z is dz. And F3 will be a function of X and Y. So ax square by 2 plus axy. So if you choose these values of these functions, you can see that all these expressions converge to the same final form. What is that final form? So let us write it here. So phi equal to ax square by 2 plus axy minus ay square by 2 plus bz, plus you can take a constant of integration also, because all these functions may include some constant, say c. Yeah. So the choice of the c is arbitrary in a sense that if you consider that at x, y, z equal to 0, phi is equal to 0, then you can choose c equal, you will get c equal to 0. So c is just a reference value. It depends on that at some given x, y and z, what is the value of phi that you take. So this problem, I mean, I try to make sure that you understand the spirit of partial integration properly. So let us solve the third part of the problem. Find the projections of the streamlines on the xy plane. Okay. So first of all, when you are considering the projections of the streamline on the xy plane, these are the only velocity components that are of concern. So you see something which is very interesting. Just calculate this. So from this u and v, therefore, so with this mathematics, actually, we have come into a kind of conclusion which we will not normally believe until and unless we see this example. From the very junior level fluid mechanics class, and in fact even what we have studied here also, one common perception is that for two-dimensional and incompressible flow, this is 0, right? This is condition for incompressibility or the kinematic constraint for incompressibility for a two-dimensional situation, it boils down to this. So that is true that for two-dimensional and incompressible flow, this is 0. But what may not be true is that if it is 0, it need not necessarily be two-dimensional and incompressible. Okay. So this second part, which I have just told, is something which I am dead sure none of you have ever thought of. What you have thought of and what you know is that for two-dimensional and incompressible flow, this is 0. But what I'm talking about is that if this is 0, there is no guarantee that it is a two-dimensional and incompressible flow. And the example is straightforward here. So you see that this is becoming 0, but it's not a two-dimensional flow. It's a three-dimensional. So for this is equal to 0, from here you cannot simply say whether it's a two-dimensional flow, three-dimensional flow, etc. Sometimes we tend to overstretch what every individual equation implicates, and by just looking into this, we make a conclusion that yes, that means it's a two-dimensional and of course incompressible. But here we show that it is not the case. But when it is expressible in this form, one of our jobs is done. What is done? So if it is expressible in this form, then you can write this parametric representation. So this parametric representation actually reflects this one rather than two-dimensional incompressible flow. See, this is one of the limitations of how we learn the fundamental definition of a subject of parameter in this subject. So when we learn the stream function, the first concept that we learned is that it's a two-dimensional and incompressible flow for which it is defined in this way in which it is. But here we can see that although it is not two-dimensional flow, compressibility, incompressibility, again it is incompressible flow, no doubt about it, but it is not a two-dimensional. It's a three-dimensional. So it is actually a three-dimensional plus incompressible, not two-dimensional. So ideally, the stream function, the way in which we put up the definition in a strict sense, would not have been valid. But here, your understanding of the way in which this parametric form came up through the derivations is important. So doesn't matter 2D, 1D, 3D, whatever. Our objective of parametrizing here was to make sure that you represent U and V by certain parametric form so that this equation is automatically satisfied. And with this parametric form, it is automatically satisfied because if you substitute, it will be 0. And in that way, this parametric form remains valid so long as this equation remains valid. Doesn't matter whether it's 2D or 3D. So that means that we are in a position to describe the projections of the streamlines on the XY plane. And to describe that, what we will simply do is we will use this function psi. We will not call it like a stream function. At the most, we can say that it's a projection of a stream function. But this is as good as the projection of a streamline in the XY plane. So I'm just integrating and writing the values of the constant of integration. So F1, F2, F3 we have used, F4. So can you tell it will be a function of what? Any one of you?
X, sir, X.
It's
First one is X
Function
and
of
second one.
x.
okay. So it's a function of x, and no question of z because we are talking about projection in the xy plane only. So this is minus ax square by 2 plus axy, and this will be a function of y. So if you just compare, you will get you can as well put a constant if you want, but again, if you take the reference that at x, y equal to 0, the value of psi is equal to 0, then from that you can conclude that that constant will be 0. Okay, so I think this example was illustrative to show you calculations which cover most of the aspects of the parametric representation of flow and visualization of flow. We will next enter into our subsequent chapter. The subsequent chapter is dynamics of inviscid flow. So in the previous chapter, we were bothered only about motion, not the forces which could be responsible for the motion. In this chapter, we will be bothering about the forces except the viscous effects, because in a inviscid flow, the viscous forces are not there. So you have to keep this in mind very, very carefully. So when we say that it is inviscid flow, that doesn't mean that the fluid has zero viscosity. It only shows that viscous stresses are not important. So or viscous forces are not important. So there could be many situations. For example, I can give you one of the very common examples. So if you just recall the Newton's law of viscosity that all of you have learned earlier in some context. So if you even take it in a very simplified form, the most simplified form, the viscous stress is the viscosity times the velocity gradient. So if the velocity gradient is 0, the viscous stress is 0. Doesn't matter whether viscosity is 0 or non-zero. So when we say dynamics of inviscid flow, we are not necessarily talking about fluid with zero viscosity, but we are talking about situations where viscous forces are much less significant or absolutely insignificant as compared to or other forces which are there. So our objective is to write an equation of motion. So when we say equation of motion, we always start with our thought process starts with Newton's laws, typically the Newton's second law. So we'll start with the Newton's second law. So this is our intuitive equation of motion. That is the first form of the equation of motion that we have learned in the school level. As I keep on telling that any concept, I would prefer to start with a school level idea, because school level idea most of the times it is intuitively correct, but mathematically not that strongly founded, because the rigor of mathematics at the school level is limited. So when we say the Newton's second law or the equation of motion, what we essentially do is we consider either a single particle or a system of particles, which together is like this, what is called as control mass system. And for this control mass system, we write that the rate of change of linear momenta is equal to the force which is acting, or in a different way, the force is equal to the mass into acceleration. So one of the prerequisites of writing the force equal to mass into acceleration in the way in which we have learned in school is that we must take a control mass system, something which has fixed mass and identified fixed mass. The challenge is that for a fluid, it is not so easy to identify that, because fluid is continuously deforming and it is not straightforward to identify. So what we will do is whether it is easy or not to identify, but we will still consider a control mass element in the fluid, and the control mass element will consider a special type of geometry so that the coordinate system based calculation is straightforward. So what we will consider is a rectangular fluid element. So rectangular fluid element, what it means is that in the three-dimensional space, the control mass or the lump of mass, whatever you call, is having this rectangular shape. Let us put up the coordinate systems or the coordinate axis. This is x, this is y, and this is z. Okay, and let us put some dimensions. Along these dimensions. So this is a fluid element. That means this is you can say momentarily we are talking about a rectangular shaped fluid mass. Momentarily, because it may be deforming, and therefore this is momentarily it is like this. So what we will do is we will write an equation of motion for this, and to begin with we will write an equation of motion along the x direction. In the kinematics chapter, we have learned how to write a very important component of the equation of motion. See, if you imagine the Newton's second law in its most naive form, it is force equal to the mass into acceleration. In the kinematics chapter, we have learned how to write an expression for acceleration. So here the only extra thing that we have to do is to write an expression for force. So what type of force is acting on this? So when you have a, say, a material, in terms of mechanics, there could be broadly two types of forces. One is called as a surface force. Another is called as a body force. So what is a surface force? A surface force is something which acts over the surfaces that are encapsulating a volume of the fluid in this case. So if you imagine this volume, you will have these 6 faces: top, bottom, right, left, and front and back. So total 6 faces. Now, what could be the forces on the 6 faces? Roughly, it could be, tangential and normal. Because the surface will have a tangent and, maybe certain normal directions. Local or global normal. Here it's a global normal because the surface is a flat surface. Now we have to understand that what are the physical origins of this tangential and normal force. The tangential force, its physical origin is viscosity. So for inviscid flow, that is where viscous effects are not important, tangential forces. Normal force could be due to viscous effect, but here viscous effect is not there. It is inviscid flow that we are considering. For the normal force calculation, therefore viscous considerations will not come into the picture. The only consideration that comes into the picture is a normal force which could act even if viscous effects are not present. And when viscous effects are not present, the fluid is either static or undergoing uniform motion. And so static fluid is one such limiting example. And when it's a static fluid, we all know from our basic knowledge in fluid statics that for a static fluid, the normal force comes from the pressure of the fluid. So in that way, for inviscid flow, we can safely say that the normal force that we are talking about here is due to the pressure distribution. Now pressure, we know by its physical nature, always acts normal to a surface and inward normal to a surface. That means it is like this and this, this and this, and maybe from the back and in the front. So from the pressure, it is quite clear that it is trying to compress the material. Now, out of all these, for the motion along X, only the forces on these surfaces are important. Why? The reason is straightforward, because these surfaces are the only surfaces where the normal is along the X direction, and therefore the pressure is also along X direction. So let us write the expressions of these forces. Other ones also we can write, but we will not write because we are writing equation of motion along X, and those forces are along Y and Z. So if you consider the left face, so the pressure say is equal to P. We are considering delta Y very small, so pressure will not vary appreciably along delta Y, or as a matter of fact delta Z on the surface, and we can just treat it locally as P. So the force is P into delta Y into delta Z. This is the force due to pressure. What is the force due to pressure here? If the pressure at the left face is P, then the pressure at the right face is whatever is given by the Taylor series expansion with pressure as the function. So if we consider the variation of pressure along x, we have just written the first order term and not the higher order terms. So this is the Taylor series expansion of pressure, which shows clearly that the role of gradient of pressure along certain direction. The area remains the same. So now let us write the Newton's second law. As applied along the x direction. So resultant force along x is equal to the mass of the element. Let us call it as delta m into the acceleration. So resultant force along x. So we can write P so this is one of the major components of the force along x, but this is not the only component, because so far we have talked about only the surface force. We have not talked about the body force. So what is the body force? Just like the surface force is distributed over the surface and therefore often expressed as force per unit area of the surface, the body force is force distributed over the volume or mass of the body. So we often write the body force as a body force per unit volume. So if Bx is the body force per unit volume along x, then what is the total body force along x? So Vx is per unit volume, that times delta x, delta y, delta z is the body force. So surface force plus body force, this is the total force. What is the mass density times volume? And here deliberately we have taken a small volume because we will set delta x, delta y, delta z all tending to 0. And if we set them all tending to 0, then this mass will shrink to a point mass, and then the density will be the density at that point where we are considering the point mass. So this is the mass delta m times acceleration along x. So let me just clean up some space. The job of our schematic is done. So now we will cancel certain terms. This one. So in that way, you have plus higher order terms were there that I did not write. So now you take the limit as delta x, delta y, delta z all tending to 0. And one of the mathematical purposes of taking this limit is to actually write a differential equation. Differential equation will be valid at a point. So until or unless you shrink the material to a point, you will not be able to write the differential equation. So when we take that limit, we can cancel this because they are tending to 0, so they are not equal to 0. And all the higher order terms which will contain some powers of delta x, delta y, delta z, that will also be 0. So you will get this very simplified equation. And we have only one step left from the kinematics chapter. We already know what is acceleration along x. So let us write that. So we have been able to write a Newton's second law expression in terms of Eulerian mathematics. This is, I think, one of the very important considerations, and inherently Lagrangian description law is expressed in terms of Eulerian coordinates. So that is why you can see this total derivative appears in the acceleration. So we can reorganize this and write just the right hand side in the left hand and left hand side in the right. So this equation we are able to also write in a more compact way. So you can write, for example, this one, where this velocity vector v is this one, capital V. So if you take a dot product of that with a nabla operator, which is or sometimes you call it del operator. So I into the partial with respect to x plus j into partial with respect to y plus k into partial with respect to z. So that is that nabla operator. If you make a dot product of that with or dot product of the velocity vector with that, you will get the three terms which are marked by red, and all the terms are operating on u. So in a compact vector, partially vector form, not completely vector form. If we now write this x component of equation of motion, we will be able to write the following. Okay. So this is x component. We can similarly write the y component. Very straightforward. So this is x. The next we are going to write y. So the only change is the operator will operate on the respective y parameters. And similarly the z. So now, if you want to write a single vector equation that includes these three components, what we will do is simply multiply this with I cap, j cap, k cap, so this also, and just add. So if you do that, I'm just isolating different terms from different equations. So v dot nabla ui plus bj plus. This is the left hand side. So this is where we have clubbed up all the like terms from the different components, and now we will write it in a single compact vector form. So the first one, so this is nothing but the velocity vector v. This is also the velocity vector v. This is by definition gradient of the scalar function pressure, and if we call this as the body force vector per unit volume, so this is what is the equation of motion in vector form. Again, the beauty of the vector form is that this is agnostic to any Cartesian or any other coordinate system, so you can convert it into whatever coordinate system form that you want just by simply replacing the nabla operator of that coordinate system, and the velocity also expressed in terms of the components of that particular coordinate system. So this is an equation of motion sufficiently general, only viscous effect is not there, and this is known as Euler equation of motion. Okay. So this is Euler equation. So the only restriction of the Euler equation is that it is invisible. There is no other restriction related to this. So this is quite a general equation. On the face, it appears to be very restrictive because it is considering inviscid flow, and many of us have an intuitive feel that there is no such flow which behaves like inviscid flow. But there are several such practical situations which I will come up with as we keep on discussing in this course. That there will be many such situations where the viscous effects are not important, although the fluid has viscosity. So you can apply this equation without restriction in that case. It was first derived by the famous mathematician Euler, and that is why it is called as Euler's equation of motion. Now what we will do is that on this Euler's equation, we will do some mathematical manipulations and then understand the physics of that outcome of that mathematical manipulation. So the first manipulation, before we do, we will consider the vector identity, because see in this equation the whole challenge is this term, because this is a non-linear term in the differential equation. Had this term being 0, it would have been a linear differential equation, but it's not. It's a non-linear differential. So let us try to apply the vector identity So this is a vector identity. We'll apply this. The generality of this identity is that it doesn't matter what the vector v is. In a fluid mechanics, of course, we are taking it as a velocity vector, but in general, it could be any arbitrary vector. So that is the generality of this. V dot v is v squared. So you can therefore write this equation. So this one plus v. So this is just another way of writing the Euler's equation. Now what we will do is we will try to apply this equation, or this form of the Euler equation along an arbitrary line segment given by the vector dl. So dl is nothing but dxi plus dyj plus dz. So we want this equation to be applicable along this line element. So to do that, we are doing the following. So we make a dot product of this one with dl. So this is the vorticity, if you recall, curl of the velocity. Okay. So our objective is to make this equation applicable along a chosen line segment, or a direction of directed line, better to say, rather than the line segment. So that directed line is dl, and we have to carefully see that what is the implication of the direction of that directed line. Before that, let us do some one more step of algebraic calculation. Okay. So now this becomes like u dx plus v dy plus w dz, like that type of term. We are not simplifying it anymore, because for the subsequent part of this derivation, we will consider a steady flow. If we consider a steady flow, then it will not matter what is the further simplified form of this. So I'll just erase this part, giving you an understanding of that. If this was to be simplified, what would have been done. But we will pay more attention in simplifying the second term, because even if it is steady flow, this will be there and it is important. So we will use the definition of the nabla operator. It operates on V square for this example, which is a scalar. So when we write this with dot of so this will be half of, so I dot I is 1, j dot j is 1 and k dot k is 1. So it will be simply, that is this term with this term. So this one. So by the law of, or the rule of the total derivative, d, so d of v square is its partial component with respect to x, partial component with respect to y, and partial component with respect to z. Similarly, the pressure gradient term. So let us clean this space up and just call it half dv square. So the pressure gradient. Dot with so this is nothing but dp. So I'm just writing this as dp. And as an example, see, V is an arbitrary body force, but the most common in our daily example is gravity. So let us imagine a situation which is very common situation we describe in mechanics, that we have a z-axis like this, which is vertically upwards, and gravity is of course downwards. So in that way, the example that we can take is V is minus, so this is body force per unit volume. So body force, so total body force due to gravity is mg. So mg per unit volume is rho into g. So density into g, but no, the direction also is along the negative x. So it is this one. Accordingly, this one will have only the dot product, the dz will be there. So that will be minus rho g dz. So let us write, reorganize all the terms and then write. So the next step, what we will do is we'll bring all the terms in one side and divide those by rho. So we'll write dp by rho.
Sir,
Yes.
sir, body force should be minus rho g dy.
No, why? I mean, I have considered it along the opposite z direction. So why y comes?
Sir, gravity is acting downwards.
Yes, but if you see, I have taken upward direction as z. So whether you will take it x, y, or z is up to you.
Okay, okay, sir.
Okay, so in this diagram, if you see here, I have taken the upward direction as z and gravity opposite to that.
Okay, sir.
Okay, so dp by rho plus d of v square by 2 plus g dz. So these three terms, why I have isolated is because these three terms will appear to be extremely close to the Bernoulli's equation, or almost like leading to Bernoulli's equation that all of you have learned at some point of time. These three terms. But there are certain extra terms. We'll keep that with a different color. So what we can see from here is that, well, we have made, what are the assumptions that we have made while writing this? What are the assumptions that have gone in up to this? Can any one of you tell?
Steady and irrotational.
Yes?
Steady and irrotational.
No, steady flow is not considered. So unsteady term is very much there.
Inviscid flow. Inviscid flow.
So two assumptions. One is inviscid flow. Another is gravity is the only body force and that acts along the negative z direction. Okay. Otherwise, there could be other expressions for the body force. So these are the two assumptions. We have not taken any other assumption. So now we will make some further assumptions. So to make it clear, I will write that what are the initial assumptions that we have made to arrive at this, and then some further assumptions. So initial assumptions. So initial assumptions were inviscid flow, and gravity is the only body force and that acts along negative z. Okay, so these are the initial assumptions. Now we will make further assumptions. So one further assumption that we will make straight away is steady flow. The unsteady flows in the same framework we will consider in this chapter itself, which normally in the undergraduate level is not covered so well. We will cover that, but not for the timing. So for the timing, we will assume that this term is not there because it is steady flow. So that means that you are having this equation. So one is steady flow. The next we will write a constant density flow. So constant density means this is like a constant, so that I will put an asterisk against this assumption, and we will show that this is of course leading to d of p by rho, because rho is a constant, doesn't matter. But I'm giving you a homework which is a bit more non-intuitive than this. So can you write d p by rho, dp by rho, this one as d of p by rho, even if rho is a variable? So I will ask an answer, or I will ask for an answer to this question in a subsequent class. But my question that I am putting forward is this, that so d of dp by rho is equal to d of p by rho. I mean, one clear case that we have considered is density is density equal to constant. But even if density is variable, not all cases, but for certain cases of variable density, can we consider that? So the hint that I want to give you is that imagine density as a thermodynamic property. So a thermodynamic property can be a function of two other independent thermodynamic properties. Say density could be a function of pressure and temperature. So imagine the case when you have density as a function of temperature but not pressure, and density as a function of pressure and not temperature. I mean, just think as these two different cases and you will get some idea of this one. The whole objective is to impress upon you that while constant density is something that we talk about, we often forget that there could be less restrictive conditions than constant density that will still make this dp by rho as d of p by rho. And the other assumption that we are taking is that this is something which is very obvious in engineering, but not so obvious if you cover all aspects of science, that g is not a function of z. So in atmospheric science, or if somebody is applying this equation to outer space, the gravity force will be a function of height. Only in a limited range of height, this g is not a function of the height, and therefore in that case, so if you consider this as double star, the double star assumption will lead to d of gz. So let me just write it here. So d of p by rho plus v square by 2 plus gz So now we can see that there are so many assumptions that have already come in. So major ones, I mean, which are so very apparent and that we call as major are this inviscid flow and steady flow and constant density flow. But the role of gravity as the only body force along negative z, and that also not a function of z. These are also to be remembered when we are writing this. So now the question is that we all know, I mean, from our previous experience that sum total of these three is something which is constant in the description of Bernoulli's equation. So if we have that as constant, then d of that should be 0, and the only sort of hindrance that is not allowing us to put that up as 0, or the only culprit, so to say, is this term. So if this term could be 0, then straight away we can say that d of this is 0 and this is constant. So let us try to figure out that what are the conditions under which this culprit, which is in general standing between this and what we call as Bernoulli's equation, that culprit will be gone, and we can say that the corresponding term is 0. So our subsequent quest is therefore that when is so there are certain trivial cases. One is the velocity is a null vector. We are not talking about that. This is not relevant. Why not relevant? Because if velocity is 0, then we are not start talking about a fluid dynamics problem. It's a fluid statics problem. So that is not relevant. But you will have another obvious case which is relevant, but obviously coming out of this. That is, so this is one, not that all of these. So this is either 1 or 2. So this is called as irrotational flow. We have seen earlier in kinematics. So for irrotational flow, this will be 0. The third one, see, remember when we are having this as A cross B dot C, so you have the corresponding determinant expression. So in a determinant, so this is like the first row is pointing towards the in the direction of velocity, and the third row is pointing in the direction of that dl, the line element, and this is pointing towards the direction of the so-called vorticity. So in a determinant, mathematically you know that the determinant will be 0 if either some rows are identical or one row is a scalar multiplier of another row. So let us consider row 1 and row 3. So row 1 and row 3, they are scalar multipliers if dx by u is equal to dy by v is equal to dz by w. Then this is like so dx you can write say cu, dy cv and dz cw. So this is c into the first row. So if this be the case, then this determinant is also 0. So that means that what is this? This is the equation of streamline. So the dx, dy, dz are special components, so that dl is along the streamline. So dl is along a streamline. But there are so this is or there is a case number 4. In fact, there could be different cases number 4, but one example of case number 4 is V cross this is perpendicular to DL. Okay. So this is a dot product, right? So it is like V cross omega, let us call it a vector A. So A dot DL. So if that is 0, that means A and DL, if they are perpendicular, their dot product will be 0. So that means, see, out of these, the velocity and vorticity you cannot really independently choose, because a fluid flow will have its natural velocity, and once it has its natural velocity, vorticity is the curl of that you cannot change. But what you can change is that you can choose your DL as per your wish. So you can, in principle, choose a DL so that these two are perpendicular. So then that is also possible. So this right hand side is equal to 0, except for the trivial case of velocity equal to 0, for either DL is along a streamline, or the flow is irrotational, or say V cross omega is perpendicular to DL. So if either of these assumptions is satisfied, so either of these assumptions is satisfied, that means not 1, but 2 or 3 or 4, then we can set this equal to 0. So this is subject to these assumptions. And then you have d of p by rho plus v square by 2 plus gz is equal to 0. That means p by rho plus v square by 2 plus gz is equal to constant, which is the so-called Bernoulli's equation. So today we do not have much more time to discuss more extensively on this, but by summarily observing this derivation, at least you must have noted that the Bernoulli's equation is not that trivial as it appears to be in high school. There are several possible assumptions. Not that all assumptions have to be simultaneously valid, but a combination of assumptions will lead to the development of the Bernoulli's equation. We'll look into those combinations of assumptions and what happens if they are relaxed, etc. very carefully, give a physical perspective to this one, and then extend it to different types of flows, including unsteady flow. We'll do that in the next class, and so let us wind up the lecture for today for the time being. But we have another 5 odd minutes. So if you have questions or any observations to share, please feel free, and we can discuss. So any one of you have any question on whatever we have discussed up to whatever? So if not, we will. Yeah, anybody having any question? The easiest way to convey your question is just raise your hand so that I will know who you are, and then anyway, if you have no further questions, we will stop the class today and we'll continue on Thursday morning as per our usual schedule. Thank you very much.